In-depth review of probability theory and its application to random experiments. Introduction. The probability theory is a branch of mathematics that deals with analysis of random phenomena. It provides the framework for quantifying uncertainty and making predictions based on incomplete information. There are some key concepts of applications of probability theory in random experiments, like random experiment, sample space, events, probabilities, independent events, conditional probability, and Bayes theorem. Uh, and there are some applications like games of chance, statistical statistical inter, in, inference, risk assessments, quality control, and machine learning. Understanding these concepts allow us to apply probability theory to various real world situations, making informed decision despite uncertainty. Historical background. The historical background of probability theory is rich uh, and spans several centuries, evo- evolving from philosophical discussions to a formal mathematical discipline. Like in the early beginnings, in the in the early beginnings, the ancient civilizations, the probability concepts can be traced back to ancient civilizations such as Egyptians and Greeks, who used the basic forms of chance in games and divination, and also in and Renaissance developments, a formalization of probability, and in 18th and 19th centuries, Paris Salmon, Salmon Laplace in 1812 further developed probability theory, introducing Bayesian methods and enhancing the mathematical framework with his work theory, analytic disk probabilities, and in 20th century and beyond, measure theory and applications and expansion. Today, probability theory is a cornerstone of modern mathematics, statistics, and many scientific disciplines, underpinning a wide array of applications in everyday life and advanced research. Key concepts in probability. Here are some key key concepts like random experiment, sample space, event, probability. Probability is P of A is equals to number of favorable favorable outcomes by total number of outcomes, and dependent events, conditional probabilities. P of A by B is equals to P of A intersection B by P of B, and Bayes theorem is P of A by B is equals to P of B by A and P of A by P of B. With the law of total probability and random variable and probability distribution and expected value, variance and standard deviation, law of large numbers, central limit theorem. These concepts form the foundation of probability theory and are crucial for understanding and applying statistical methods. Types of probability. Probability can be categorized into several types, each serving different contexts and interpretations. Here are some main types. Uh, Theoretical probability. This is based on assumption of equally likely outcomes, and it is calculated using the formula P of A is equals to number of favorable outcomes by total number of outcomes. Second one, experimental probability. It is based on outcomes of a actual experiment or observation, and it is calculated as P of A is equals to the number of time events A occurs by total number of trials. Third one, subjective probability. This type is based on a personal judgment, eh, or experience rather than precise calculation. And next one, conditional probability. It refers to probability of an event occurring given that another event has already occurred, and it is denoted by P of A by B, and it is calculated as P of A by B is equals to P of A integration B by P of B. Next one, joint probability. This is a probability of two events occurring simultaneously, and it is denoted by P of A integration B. Example: the probability of rolling a 3 on a die and flipping it on a coin at the same time. Sixth one, marginal probability. This is the probability of a single event occurring irrespective and the outcome of another event. It is obtained by summing or integrating joint probabilities. The seventh one, cumulative probability. This represents the probability and the random variable takes on a value less than or equal to a specified value. It is useful in continuous distributions. Example: in a normal distribution, the cumulative probability for a certain z, score indicates the probability that a value falls below the score. Understanding these types of probability helps in selecting the appropriate methods for analyzing random phenomena in various fields. This probability distribution describes how probabilities are assigned to different outcomes, and common distributions include the normal, binomial, and Poisson distributions, each serving specific applications in statistical analysis. Random experiments defined. A random experiment is a process or action that produces outcomes that cannot be predicted with certainty. Each time the experiment is conducted, it may yield different results even under the same conditions. The key characters are uncertainty, reproducibility, a defined sample space. Examples of random experiments are coin toss, flipping a coin results in either heads or tails. Second one, dice roll, rolling a six-sided die results in one of the numbers 1 through 6. Drawing cards, drawing a card from a card from a shuffled deck results in one of 52 possible outcomes. The weather observation, measuring whether it will rain tomorrow is an experiment with uncertain outcomes. These random experiments form the basis of probability theory as they help define events and sample spaces, allowing for the calculation of probabilities associated with different outcomes. Law of large numbers. The law of large numbers, LLN, is a fundamental theorem in probability theory that describes the result of performing the same experiment a large number of times. It states that the number of trials of a random experiment increases the sample average or sample mean of the results will converge to the expected value or population mean of the underlying probabilities distribution. There are some key points like sample mean convergence, the law that asserts the average of the outcomes from a large number of trials will get closer to the expected values of the number of the trial increases. Types: weak law of large numbers, strong law of large numbers. Practical implementations: examples like if you flip a flip a coin many times, the proportion of heads will converge to 0.5. If you roll a die repeatedly and the result will converge to 3.5, the expected value for a fair die. Importance: the law of large numbers is crucial in statistics and probability, underpinning many statistical methods and justifying the reliability of estimates, large sample estimates. It assures that it assures that randomness averages out to overcome, leading to predictable outcomes in the long run. Central limit theorem. This central limit theorem asserts that that there is a distribution of sample means approaches a normal distribution as sample size increases, regardless of the original distribution. This theorem is pivotal in statistics and data analytics. Applications in real life. Applications in real life. There are some key examples: insurance, quality control, polls and surveys, finance and investment, sports, insurance premium calculation, a game theory gambling, marketing analytics, and machine learning. These applications demonstrate how the law of large numbers helps in making informed decisions and predictions by leveraging the power of large samples to stabilize the outcomes. Challenges in probability. Probability theory with a powerful tool for understanding uncertainty presents several challenges in its application and interpretation, like understanding of probability concepts, misuse of probability, sampling bias, overfitting in data analysis, rare events, independence assumptions, Bayesian versus frequent perspectives, complex systems, ethical considerations. Addressing these challenges requires careful consideration of methodologies, clear communication of concepts, and ethical awareness in application. Future directions. The future direction of probability theory and its application is likely to be shaped by several emerging trends and developments. Here are some key areas to watch: integration with machine learning and AI, big data analytics, probable, probabilistic programming, complex system modeling, inference, ethics and fairness, interdisciplinary collaboration, real time decision making, and educational advances. Conclusion. This, in conclusion, the probability theory is essential for understanding and analyzing randomness in domains. Various domains. Understanding and understanding the cons and understanding the concepts such as random experiment, sample space, and the law of large numbers provides the tools needed to analyze the real world situation and make informed decisions. Ultimately, a deeper understanding of probability will empower individuals and organizations to navigate uncertainty more effectively, leveraging data driven insights to improve outcomes in fields ranging from finance and healthcare to engineering uh, and social sciences. The future of probability theory is bright, promising, promising, exciting developments that will further enrich our ability to interpret and act upon the complexities of the world around us. and thank you.